RoMan Manufacturing creates products that provide the best power delivery in resistance heating. They approached Grand Valley School of Engineering in hopes to create a cost-effective power control unit. With such a large vision in mind, they intend for this project to be continued by future senior project teams at GVSU.
Our project scope is to create the foundation for future development of this power control. What we must do is take in three-phase 480 volts from the power grid and convert it to a single-phase 650 volts at 50 amps output so that it can be useful for RoMan Manufacturing's customers, which may use our project for continuous resistance heating. This power conversion must be done through an active rectification process using silicon-carbide MOSFETs, which are more efficient than traditional passive diodes or active IGBT switches. After the rectifier, the voltage will be converted into discrete voltage, which is smoothed out using a capacitor bank. After the DC capacitor bank, the power travels through the inverter circuit, which takes the newly created DC voltage and inverts it into a single-phase square wave. In a circuit, high current correlates with high temperature. So in order to prolong the lifespan of our project and its components, a water-cooled chill plate is implemented. The chill plate has a copper pipe embedded within the aluminum plate. This pipe is used to carry chilled water through the plate, which will help cool the attached components. The third and one of the larger portions of this project includes software development. The rectifier algorithm must read the three-phase voltage and detect the peaks for each phase, and switch the MOSFETs according to which phase peak is high or low. The other algorithm required is for the inverter MOSFET switching. Both of these algorithms and processes are highly critical because if the wrong MOSFETs are activated, the power could be shorted to ground. The worst case scenario would be the power shorting to ground, which would blow up our components and have the possibility of harming nearby users. The software has to control the circuit as well as monitor the temperature and different voltage and current values. If any voltage, temperature, or current exceeds our specifications, then we must properly shut down the circuit. To handle all of the control requirements for the software, corresponding hardware was created to make our software algorithms a reality. 4 printed circuit boards were designed to step down our voltage and current to be measured by our microcontrollers, signal any faults or statuses through LEDs, and provide power to circuits that will drive and monitor our output power circuit. Dealing with dangerous power is new for most of our group members. Along with the learning curve, we had to deal with component shortages, which delayed our timeline and algorithm development in software. The problems we faced through the past 2 semesters have led to a delayed project where testing is still underway. Since this project is highly dangerous, our testing procedure is lengthy and detail-oriented. A large portion of our testing procedure has to do with maintaining a safe environment for the users and our components. A lengthy testing process has been implemented with the overview of RoMan Manufacturing employees, which will monitor the output waveform, temperature, control, and the power of the device under operation. Upon the completion of testing, RoMan will continue development and will likely utilize the senior project program at Grand Valley in the coming years. So on the left side of the screen, you can see that we have a 3-phase input that goes into our rectifier, goes to a DC bus, which is rectified at the peak of our voltage input. So in the case of 480 volts, that is approximately 678 volts at the peak. With some losses, we estimate a conservative 650 volts, which is then inverted using our MOSFETs switching at 1000 Hertz to an AC wave shape that can be then put into an MFDC RoMan transformer, which is then output to a heating element to allow the resistance heating process to operate for the customer. Here you can see the black box diagram for our system, which summarizes the inputs and outputs. The entire control system is powered by 24 volts DC, and the power circuit is provided 3-phase 480 volts. There is water input and output for the cooling system, and the power circuit is controlled using a set point voltage and a system enable switch, in addition to other parameters that are loaded onto the circuit. On the output of the power circuit, we have single phase voltage in the form of a square wave for this prototype, as well as data such as system input values, the control status, system outputs, and temperature status. Heat will also go in and out of this system. While this project is just the beginning of the product development, the final product scope looks to have 2 models available for RoMan's customers. One providing 300 amps at a full voltage output, and the other providing 600 amps at a full voltage output. This output voltage is based on the 3-phase input provided, ranging anywhere from 300 volts RMS to 650 volts RMS at either 50 or 60 hertz. On the output side, there are 2 output modes, each with their own frequency range. Square wave, ranging from 400 hertz all the way up to a possible 10 kilohertz, or a sinusoidal approximation, ranging from 40 hertz all the way up to 200 hertz. In addition to these different wave shape outputs, customers will be given the option of controlling their set points based on maintaining voltage output, current output, or a constant power output.